5, 4, go for main engine start, 3, 2, 1, 0, and ignition and liftoff of the Atlas V with the Solar Dynamics Observatory.
February 2010. NASA launches its most sophisticated solar satellite yet. The Solar Dynamics Observatory, or SDO for short.
Coming up on Mach 1.
SDO is the first satellite to deliver almost continuous, super high resolution coverage of our nearest star, giving researchers unprecedented access to the sun and its secrets.
The first day was very exciting. We knew we were going to open our doors to actually let the sunlight into the instrument for the first time.
We started looking at the first pictures, and it was almost in focus. And as soon as we focused it, it was just beautiful.
The new images reveal the sun like never before. An alien landscape where strange structures ebb and flow. Giant tornadoes, hundreds of thousands of miles high, that could easily engulf the Earth. And superheated bubbles of plasma the size of Alaska.
When I look at the pictures, I think they're really beautiful. I'm struck by the dynamics of it. Things are changing all the time, no matter where you look. And I'm also pretty daunted by the complexity of it all.
That's not surprising. Previous satellites only revealed a portion of the sun in high resolution. Now, they see it in mind-boggling detail.
Now, in order to look at the Solar Dynamics Observatory images that we're bringing in every day, we've built this very special wall, which is 9 high-definition television screens together that can display these images, so that the instrument and the display system together are an entirely new way of looking at the sun.
We can see all the details of what is going on, and that is really a quantum leap in solar physics. Being able to see all of that all the time, a continuous eye on the sun.
One of the most important aspects of SDO is its ability to see sunlight across a range of wavelengths, the equivalent of looking at things glowing at different temperatures. Our eyes are most sensitive to sunlight glowing at around 10,000 degrees Fahrenheit. At this temperature, the sun's surface looks almost featureless. But at hotter wavelengths, normally invisible, a far more dynamic picture emerges. The February 15, 2011 storm is a perfect example. In this repeating image, at around 90,000 degrees Fahrenheit, SDO captures just a ghostly trace of the CME wave. But at just over 1,000,000 degrees, the superhot plasma rippling away from the eye of the storm is much clearer. This allows researchers to see coronal mass ejection waves evolving across the entire sun.
This is an absolutely amazing time for solar physics because of these beautiful high-resolution images that allow us to understand better the physics behind what's going on when solar storms erupt.
There's that one last photo. Look at this one here.
Back at the National Space Weather Prediction Center,
That's the M1 here.
Bill Murtaugh tracks the storm's CME wave. It carries 1 billion tons of plasma and is now only about 20 hours from Earth.
We're bringing it in mid to late on the 17th into the 18th.
What they see is alarming.
Well, there's actually 3 CMEs that we're looking at. So we bumped up some numbers for late tomorrow. Yeah.
It's not a single CME wave. but 1, 2, 3 of them.
We won't call it the perfect storm yet or anything, but conditions are lining up for some significant space weather.
Their models show trajectory and speed, but the big unknown for Murtaugh is how powerful the waves will be when they hit. The answer lies in a force that governs the sun: magnetism. We're all familiar with magnets. They produce an invisible force that pushes and pulls on charged particles. In fact, Earth has a magnetic field that protects us against threats from the sun. But we are less familiar with the sun's magnetic power, which researchers believe plays a major role in driving solar storms.
We've essentially learned that it takes two things to make a star magnetic. It needs to have these convective motions right underneath the surface, the bubbling of the gas. It needs to spin, and the faster it spins, the more active it becomes. And wherever those two things, the bubbling and the spinning, can interact, that's where we see the strongest magnetic activity in stars.
Astronomers know that the surface of the sun spins in a strange way. Travel from the poles of the sun towards its equator, and you'd notice it turns faster. Analyzing sound waves inside the sun reveals that the plasma layers beneath the surface also spin at different speeds. That's because they act like fluid, which gets denser towards the core. The interior of the sun is a place of spectacular turmoil. Turmoil that's the key to the sun's magnetism.
The motions there, the convection, the differential rotation, the motion from equator to pole, are driving a new force. They're driving a magnetic field. There's a dynamo at work here. A dynamo that's generating a force that we actually experience here on the Earth.
It works like a giant wind turbine. Churning plasma in the convection zone stirs up powerful electrical currents, which generate a huge magnetic field.
Have upflows here and downflows coming down this way, right?
The holy grail for scientists is understanding exactly how this dynamo generates solar storms. The clue lies deep within the convection zone. Magnetic field lines normally run from pole to pole. But with all the turmoil in the convection zone, that pattern can't last. Rotating layers stretch them horizontally. Convection twists and braids them. Under immense strain, they begin to kink upwards towards the surface.
Imagine this spring is a magnetic field line. The magnetic field inside the sun is amplified, is strengthened by the rotating motions and the shearing motions and the churning motions inside the sun. It wants to expand upwards, and it does, until it pokes out through the surface of the sun.
Tracking invisible field lines is normally impossible. But plasma plays a critical role.
Even though the magnetic field lines themselves are invisible, the plasma, which is heated and hot, can light up along these paths. In maybe the same way, you could think of a highway, and at night you wouldn't see the highway at all, but with the cars with their headlights on, you'd see the path of the highway.
Watching field lines is critical to understanding solar storms. As field lines emerge, they form loops. One end has a positive pole and the other a negative pole. Churning plasma beneath the surface twists these loops, pumping them with energy. If twisted enough, positive and negative parts of the loops cross. When they do, they short circuit with a tremendous explosion. The energy released heats the plasma to millions of degrees, resulting in a spectacular solar flare. It's the final dramatic stage of a very long journey. Photons formed in the core make their way to the surface. Some pass directly into space as sunlight. But in the process, that surging energy disturbs the convection zone, generating a magnetic field. The field lines wind up to the point that it explodes in a solar flare. Now, SDO provides a complete and unprecedented picture as these events evolve.
This is beautiful because the hot gas outlines the magnetic field lines that we would otherwise not be able to see. And here you can see even a twisting structure as some of the mass drains back down to the surface, and a lot of it escapes in the eruption. This is the essence of space weather, or solar storms.
This explains how flares form, but it's not the end of the story. Crossing magnetic field lines can cause nets of plasma to be flung into space. This is a coronal mass ejection, a CME wave. The portrait of how solar flares and CME waves form is coming into focus. But a key question remains. CME waves can travel 93 million miles to Earth in a matter of hours. So what gives them such explosive energy? Part of the answer is hidden here in the sun's atmosphere, the corona. It's made of superhot plasma that blisters at over 3 million degrees Fahrenheit. 300 times hotter than the sun's surface. Some scientists suspect that this heat powers massive gusts of energy that blast CME waves toward Earth at incredible speeds. But why the corona is so hot is an enduring mystery.
Understanding it's essential if we want to get to the bottom of how the sun drives space weather and the impact of the sun on the Earth.
The fact that the corona is so much hotter than the surface flies in the face of physics.
The sun's corona is a very odd place. Take this fire, for example. As I put my hands close, sure, it's warm, but as I pull them away, it gets cold. That's not the case on the sun at all. As you go in close, it's definitely warm, but as I pull away, it actually is warmer still.
Recently, Japanese investigators observe high-velocity jets of plasma shooting up from the near surface. McIntosh suspects these jets deliver heat to the corona, but he doesn't have a way to confirm it visually until he turns to SDO for help.
Lo and behold, we actually managed to join the dots and see, yeah, these objects that we could see moving out of the lower atmosphere at high speeds, kind of like these licks of flame really were reaching a couple of million degrees. It was really a tumultuous moment. We kind of looked at each other and said, wow, what have we just done?
They've shown that the plasma jets accelerating upwards from near the sun's surface generate tremendous heat. As a result, temperatures in the corona soar to 3.5 million degrees. If confirmed, it represents a huge leap forward in understanding CME behavior. The immense heat of the corona acts like a wind in a raging gale. It's constantly pushing on the plasma draped on the field lines, billowing them out like sails pulling on a mast. Like solar flares, when magnetic lines cross, there can be an immense explosion. In this case, the lines are cut and the sail whips off into space. Loaded with 1 billion tons of highly charged plasma, the CME wave can wreak havoc on electricity-dependent Earth. At the National Center for Atmospheric Research, this violent event is captured by satellites.
Now, to see the CME, we need to create a little artificial eclipse. To do that, we block out the light from the disk of the sun, and that's this little circle here. But what that allows us to do is to see this extremely faint, high-speed thing shooting away from the sun. This one moves at about 1,000 kilometers per second.
By enhancing the picture and slowing it down, it's possible to see the shockwave moving at over 2 million miles per hour. Though we have a better understanding of what causes solar storms and how they reach us, there is still a final pressing problem.
Trying to predict when solar storms are going to occur on the sun really requires a lot of detective work. Basically, we're looking for clues in observations to tell us when potential storms might occur.
The best clue comes from these. Sunspots. Dark patches which can linger on the sun's surface for weeks at a time.
A sunspot is a massive region, several times the size of the Earth, which appears on the sun as a dark spot. It's dark because it's relatively cool compared to its surroundings. And it's cool because the magnetic fields are so strong that they're suppressing the flow of heat from below.
The strong magnetic fields which create sunspots are the breeding ground for solar storms. The challenge is trying to decipher a pattern for when and how many will appear.
As we watch sunspots over a period of many years, we see something very interesting. The number of sunspots at any given time will wax and wane over a period of about 11 years. And since we now know that sunspots are associated with strong magnetic fields, this tells us that the sun's magnetic fields are likewise going through a cycle.
The constant churning and twisting inside the sun creates a powerful dynamo, the biggest electrical generator in the solar system. The magnetic field lines it produces get so wound up that roughly every 11 years, the magnetic poles of the sun reverse. After that, calmer magnetic activity prevails and fewer sunspots form, a period called solar minimum. But because of the sun's turbulent nature, the field gradually winds up again. As it does, magnetic outbursts are far more common, a period called solar maximum.
The solar cycle actually determines the personality of the sun. During solar maximum, it can get very angry and it can throw off solar storms that are sometimes directed at the Earth. And during solar minimum, it becomes much more subdued. There aren't as many sunspots, there aren't as many solar storms occurring. The activity cycle basically determines how the sun is going to act.